Hello, this video is on pH and logarithms. I want to do a little bit of a video on logarithms. I find a lot of students have difficulty with logarithms, and I think that it starts with, why do I need to know about logarithms, and what's their purpose? Well, the purpose is that if we're looking at a graph, maybe and you're used to seeing things like this, or increments of 1. So let's say we have some units of 1 here, and we have some units of 1 here. And you say, okay, something's growing at a rate of 1, and then if we double it, it's 2. And then if we have 3 of them, it's 3. Something like that. So we get a nice line like that. But a lot of times in nature, things are not additive. They grow exponentially. And what I mean by that is, let's say you start off with 1 and it splits into 2 others, and those 2 others split into 2 others, and this one over here splits into 2, and then this one splits into 2, and this one splits into 2, and this one splits into 2, and this one splits into 2. So here you started with 1, and you end up with 1, 2, 3, 4, 5, 6, 7, 8. Yeah, I've got one too many there, right? All right. So this is after 1, 2, 3 trials. We've gone to 8. And then you could go on and fill this out, and you can see that this isn't a nice one-to-one relationship. This is an exponential relationship. So for exponents, what we do is we think of things in growths of 10. So we start off with 10 to the 0 power, and 10 to the 0 raised to the 0 power is 1. So this is an exponent, this 0. That's what it's called. And 10 raised to the 0 power, that's the base. We say that's 10 to the 10 raised to the 0 is 1. And then 10 raised to the first power is 10, and 10 raised to the second power is saying 10 times 10, which is equal to 100. And then we could go 10 raised to the third power, and that would be 10 times 10 times 10, which would equal 1,000. But the thing is, we don't like writing that all out like 1,000 or 100, so we use exponents. All right? So the advantage of exponents, it's more compact, it's easier to read. We can go the opposite of that. We can, let's erase this graph here. We can also make numbers less than 1. So if I have 10 raised to the negative 1 power, that's 1/10. All right? And then 10 raised to the negative 2 power is 1/10 times 1/10, which is 1/100th. So just like the inverse of addition is subtraction, and the inverse of multiplication is division, there has to be an inverse for the exponent. And the inverse for the exponent is a logarithm. All right? So let's take something like the log of 10 raised to the 0 power. So what this log is the inverse of an exponent. So when I take the log of 10 raised to the 0 power, I get 0. Now, a lot of times you see this written in a textbook as log of 1. What is the log of 1? It's equal to 0. But see, when you see it this way, you have to translate that 1 means 10 to the 0 power. All right? So log of 10 raised to the second power is equal to 2, or the log of 10 raised to the negative 1 power is negative 1. So you say, well, again, why do we need to know this? Why is it so important? Well, let's take your coffee, for instance. So we've been talking about pH in Chemistry 140. And we know that the pH of coffee is approximately 4. What does that mean? Most people don't know what that means. They know, most people, if you ask most people, they know pH 7 is neutral, and they know pH is less than 7 or acidic, and pH is greater than 7 or basic, but that's about it. Well, what you're saying is when you have a pH of 4 coffee, you're telling me that the hydrogen ion concentration, which is what makes an acid have its acidic properties, is 1 times 10 to the negative 4th moles per liter. Now, most people don't know what moles per liter are unless they've had a chemistry class. So that's why we like this number. People can at least say, oh yeah, it's pH of 4. And they know it's acidic, but that's about as far as they go with it. Well, a lot of people think that pure water, or they know that they think pure water is pH 7, which is neutral. All right, so that tells us that the hydrogen ion concentration is equal to 1 times 10 to the negative 7th moles per liter. All right, and so here's water at pH 7, and here is coffee at pH 4. How many times more acidic is coffee than water? Well, people say, well, it's just 3 pH units. That's no big deal. 3 pH units, pH 4 versus pH 7. But what most people don't realize is that that change in 3 pH units is a change from 10 to the negative 7th power to 10 to the negative 4th power. And that is a difference of 10 to the 3rd power. All right? 10 to the negative 4th is 10 to the 3rd times stronger than 10 to the 7th, negative 7th. And 10 to the 3rd, translated into an expanded number, is 1,000. So your coffee is 1,000 times more acidic in the hydrogen ion concentration than water is. And you go, well, so what? Well, this causes erosion of the enamel on your teeth. So, orange juice is even more acidic than coffee. If you drink orange juice and coffee every day throughout your life, you'll probably notice that your enamel starts eroding, especially around the gum lines. You'll see these divots. And that's can be caused by too much acidic juices and coffees and pop and things like that, and then not brushing that away, or not rinsing your mouth out with water to neutralize that the acidity. All right, so what we need to know about pH in Chemistry 140 is that it starts with this equation. Water will react with itself, and it will form the hydronium ion and the hydroxide ion. So what's happening here is this water is donating a hydrogen ion to this water molecule, and that water molecule is becoming the hydronium ion. Now, the hydronium ion is what gives an acid its acidic properties. The sour taste, the changing the blue litmus to red, being able to generate carbon dioxide gas when added to carbonates, like calcium carbonate. Maybe you've taken a piece of chalk or something like that and added it to vinegar. Or maybe you've taken sodium bicarbonate, Arm & Hammer baking soda, and you add vinegar to it and it fizzes. That's the carbon dioxide coming off. And then what's left over of this water molecule is the hydroxide ion. All right? And this reaction is so important, it's got its own name. It's called the autoionization of water. All right? Or maybe I should just say water. And this is aqueous, it means dissolved in water, and this is aqueous, dissolved in water. Remember, this is pure over here. H2O is just a liquid here and here. All right, so if we write the equilibrium expression, we learned how to do that in the previous chapter. The equilibrium expression, constant K, capital K, is equal to the concentrations of the products over the reactants. But since the reactant's a pure liquid, and pure liquids are their concentration does not change appreciably through the course of the reaction. It's integrated into the equilibrium constant itself. So this is the equilibrium expression for the autoionization of water. Now, some people write this equation above like this. They just say H2O becomes the hydrogen ion and the hydroxide ion. And actually, something I need to do is add, it is an equilibrium, so you should have the double arrows like so. So in this case, K equals just the hydrogen ion concentration times the hydroxide ion. You're going to see these two used interchangeably. We liked writing it this way because it's easier to write. So you're probably going to see it mostly like this, but in reality it's more like this up here. All right? So just know that these are both the same equilibrium expression. All right, so what we know is this, that I'm going to write it the easier way. We know that in pure water that's neutral, that the concentration of the hydrogen ion is 1 times 10 to the negative 7th molar. And the concentration of the hydroxide ion is 1 times 10 to the negative 7th molar. All right, so if we multiply these two numbers together, remember you add the exponents. So what you would get for an answer here is 1 times 10 to the negative 14th. And we don't write the molar down because you can get something like molar squared units, and those units are meaningless to us. That doesn't really have a meaning for us. All right, so at 25 degrees Celsius, K, the equilibrium constant for water, also called the ion product constant for water, that's the more correct term, K here, is equal to 1 times 10 to the negative 14th. Yeah, let's make the 14 a little better here. All right, so remember what we learned about equilibrium constants. They remain constant as long as the temperature remains constant. So we assume all reactions that we are doing are at 25 degrees Celsius, and that K will always be 1 times 10 to the negative 14th at 25 degrees Celsius. So you say, what does that do for me? Well, if we look at a table of hydrogen ion concentrations and hydroxide ion concentrations, we just found out that 1 times 10 to the negative 7th for molar for the hydrogen ion, this has to be 1 times 10 to the negative 7th molar for the hydroxide ion. So if we increase the hydrogen ion to 1 times 10 to the negative 1 power, so this is 1 times 10 to the negative 1 molar, what does this have to be, the hydroxide ion concentration, in order to reach the equilibrium constant K here? Because that's what everything over here has to equal 1 times 10 to the negative 14th. Well, this has to be 1 times 10 to the negative 13th. So that when I multiply this times this, I will get 1 times 10 to the negative 14th. So that's the relationship between hydrogen ions and hydroxide ions. So if the hydroxide ion is decreased to, say, 1 times 10 to the negative 12th, that's a much lower concentration than 1 times 10 to the negative 7th, then the hydroxide ion concentration has to be 1 times 10 to the negative 2. So that when I multiply this times this, I get 1 times 10 to the negative 14th. Now, it doesn't always work out that way. Maybe I've got something like 2.3 times 10 to the negative 5th. What's my hydroxide ion concentration? And you go, well, I can't tell just looking at it. But I can solve a problem. I can say that I know that K is 1 times 10 to the negative 14th. I know that my hydrogen ion concentration is 2.3 times 10 to the negative 5th. Oops. What I don't know is the hydroxide ion concentration. So that's what I want to solve for. The hydroxide ion concentration is going to equal 1 times 10 to the negative 14th divided by 2.3 times 10 to the negative 5th. Yeah, I lost my 5 there, didn't I? All right. So on your calculator, the way that you would work this problem out is you would say 1 and then you would hit the exponential key. That would either be EE like this if it's a Texas Instrument, and it may be that this is a second function. It means you have to hit another button to get to this. It's above a key. So here you put in 1 exponential, then hit there should be a little plus negative key on your calculator, so 1 exponential negative 14. All right. Then you're going to divide that by 2.3, hit the exponential key. 2.3, hit the exponential key. Negative 5, or 5, all right? And you should get for an answer 4.34, or 35, let's say 35. Round that up. 4.35 times 10 to the negative 10th. All right. Actually, we'll only have maybe 2 significant figures, so you just say 4.4. How about that? 4.4. 4.4 times 10 to the negative 10. So that's what we now know the hydroxide ion concentration to be. 4.4 times 10 to the negative 10th. Does that make sense? Yeah, because look, this falls in between here and here, and this falls in between here and here. And if we multiply 2.3 times 10 to the negative 5th times 4.4 times 10 to the negative 10th, we should get pretty close to 1 times 10 to the negative 14th. All right? So, autoionization of water gives us the ion product expression for water. A lot of times this K has got a little subscript W to show that it's specifically for water. K is called the ion product constant, which is 1 times 10 to the negative 14th at 25 degrees Celsius. So you go, what does that have to do with pH? Well, like I said, most people don't know anything about exponents unless they've had a chemistry class. And so we want something that's a lot more manageable than these exponents. So pH stands for negative log of the hydrogen ion concentration. So what does the log do? Well, it works on this number. It takes that 10, it takes the exponent, the negative 12, out of the exponent, puts it into the base. So when I take negative log of 1 times 10 to the negative 12, the negative log of 1 is 0, so it doesn't, this number goes away, right? Okay. So now we're just looking at this, 10 to the negative 12, and we know that log is the inverse of 10, so that's going to bring the negative 12 down to the base. So we get negative 12, but then we got a negative here on this pH. So that's going to make that a positive 12. So the way we write this is we say, if you had 1 times 10 to the negative 12 hydrogen ion concentration, you would have a pH of 12. And people know pH 12 is basic and not acidic. Same thing here. This one becomes, if you put this number into this part of the equation, you would get 7, because negative, you get a negative 7, then the negative log makes it a positive 7. This one down here becomes a pH of 1, which is highly acidic. Now, it gets a little tricky with this 2.3 here. How do we do that? Okay, so on your calculator, it depends on what kind of calculator you have. Some calculators, you put this number in, then hit the log button, then change the sign. Some calculators, like a TI-82 or beyond, you'd put in just like you'd see it. You'd say negative log, so look for log on your calculator. You'd put in 2.3 exponential negative 5, close the parenthesis, hit equals, and you would get 4.64. 4.64. That would be the pH for this concentration of the hydrogen ion. All right. So plug that number into this. So negative log of this number raised to this power using the exponential key, you should get 4.637, which would round to, or 4.638, which would round to 4.64. All right, so let's put this all together. So we start off with the ion product constant of water, Kw, has to be 1 times 10 to the negative 14th. And that is equal to the product of the hydrogen ion concentration times the hydroxide ion concentration at 25 degrees Celsius. pH, we're focusing strictly on the hydrogen ion concentration, is equal to negative log of the hydrogen ion concentration. And let's say you're given the pH and you got to find out what the hydrogen ion concentration is. Well, you just take the reverse of that. So you would get the hydrogen ion concentration is equal to 10 raised to the negative pH. So if somebody says the pH is 5.5 and they ask you to find out what the hydrogen ion concentration is, you would say the hydrogen ion concentration is 10 raised to the negative 5.5 power. So on your calculator, you'll see right there where the log button is, you'll see maybe as a second function a 10 to the x key. So you would go 10 to the x, and then you go negative 5.5, and close the parenthesis, hit enter, and you would get 3.16, or let's say we only got... really only have one significant figure here. Let's see. We'll just say 3 then. 3 times 10. And you go, why is it one significant figure? It's only the digits after the decimal that are significant figures. This has to do with the power of the number, the digits to the left of the decimal. So really we only have one significant figure, so this would be 3 times 10 to the negative 6. That would be the 3 times 10 to the negative 6 molar hydrogen. That's the hydrogen ion concentration. All right. If you want to get a little fancy, you could also find pOH. I don't think your book actually tells you to do that, but that would be the negative log of the hydroxide ion concentration. And you could also find the hydroxide ion concentration by taking 10 raised to the negative pOH. The only reason why I show this is some people like this. If you add the pH plus the pOH together, it must always equal 14 at 25 degrees Celsius. So if I know the pH is 5.5, then I know the pOH is I should do this in my head, but I just don't really feel like it. 8.5. So I know that this has to be 8.5. So then when I add this together, it gets 14. Okay. All right. Let me do one question one of my students requested. This is problem 271 in the book. Let me see if I can find that real quick. Let's see. Make sure I get the right problem here. It's on page 271. All right, so let's look at it. All right, so this is really the same type of problem. So what this problem is saying is that it says the measured pH of a sample of lake water is 6.40. So they want to know what the hydronium ion concentration is. So it's this type of problem. They want to know what this concentration is, the hydronium ion concentration. And that's going to be equal to 10 raised to the negative pH. And again, so you look at this equation I've written here, and you look at this equation, these are the same equation. Again, we're just substituting hydrogen ion for hydronium. Hydronium is more correct, but again, for shorthand purposes, we generally just write the hydrogen ion. So for this problem, the lake water is 6.40 for a pH, so they want to know what the hydronium ion concentration is. So you would say 10 raised to the negative 6.40. All right? So on your calculator, you would look for a 10 to the x key. Again, on my calculator, the way it looks is this, is you've got a button that says log, and then above that button is a 10 to the x key. So on my calculator, there's a second key up here towards the top left. I have to press that, which activates this. So I would hit second function log, and when I do that, I should get a 10 with a caret symbol and a parenthesis. And then I would put in a negative 6.40 and close the parenthesis. So put in not the subtraction sign, but there should be like a positive negative key on your calculator, generally along the lower register or something like that. So 10 raised to the negative 6.40. Close the parenthesis, hit enter, and I get for a hydrogen ion concentration 3.98 times 10 to the negative 7th molar. All right. Now, how many significant figures should I have? Well, this has 2 beyond the decimal, so I should have 2 here. And so this 8's greater 5 or greater, round up. So my final answer should be 4.0 times 10 to the negative 7th molar. All right. So that would be the hydronium ion concentration. All right. So just to recap, this is the important equations you need to know in order to do the pH problems in Chapter 8 of our book. And you need to know how to use the calculator. And again, it depends on what kind of calculator you have. I'm using a TI-84, so I put it in just like I see it, but I do have a TI-30. Now, on a TI-30, what I would have done is I would have put this number in first, negative 6.40, and then I would have hit the 10 to the x key button on the calculator, and it would have put out the same number as that. So it depends on your calculator. Is it you put it in just like you see it, or do you put in the number first and then the function? All right. So I hope that helps. You do need to practice doing the calculations. This is an important part of this chapter, is to be able to do the mathematical applications of determining pH or hydrogen ion concentration. Why? Because this is the kind of stuff you do if you were working as a pool technician. You have to go out and measure the pH of the pool water, make sure it's at the correct pH, and then there's other tests to see what the concentrations of the chlorine and other ions are in your solution. All right. Hope this helps, and we'll pick it up later. Thank you.